So very naive piece. Traditionally, a doppelganger is something that looks exactly like you, right? And in the book, I tell the story of my mum's cousin Gerard, who claimed his dad had seen his doppelganger. In Irish legend, that meant that you were going to die, and then he died a week later. So this was many years ago. But anyway, the I guess in some sense you can say, well, what is a doppelganger? Is it somebody who just looks like you, or is it somebody who actually is exactly you? What do we mean by exactly you? Do we mean that it's in exactly the same quantum state, or do we mean that it's some sort of, because you're a macroscopic object, are we thinking about some sort of, do we really care about whether the electrons in between, are spinning up or down in your sort of small intestine? Do they have to match with your doppelganger? Is that do we need that level of accuracy, or are we happy to average over some of that discrepancy? And so, in some sense, you could think about an exact copy, literally an exact copy where it's literally in the same quantum state. But you can never really sort of probe that, because you've got to try and identify what state you're in, right? And if I'm going to take you, Robinson, and trying to figure out what's your exact quantum state, I'm sorry, but I'm going to have to vaporize you, right? Because I've literally got to sort of figure out what the state of every single degree of freedom that makes you up is in. I'm going to vaporize you, destroy you anyway, so it's not ideal. But anyways, so very loosely, we're talking about an exact copy to some approximation, and you can sort of speculate how accurately you want that to be, and you can make it really accurate in principle.
Yeah, so maybe a good way to start is with this just naive formulation of the problem. And as I understand it, it is, if the universe is extraordinarily large, far larger than the observable universe, which it presumably is, then certain configurations of matter will recur, and naively, my doppelganger, without getting into what actually constitutes a doppelganger, just something that is me, will be found as we look farther and farther away from Earth, because these configurations will recur just because of the immense amount of mass in the universe. And the question is, how far away do we have to look before we will find my doppelganger? Would you say that that's a reasonable way of putting the problem?
I wouldn't talk about mass, but with that caveat, yes, I think that's fair enough. Yeah, I think it's really the question of, so you look at the sort of volume of space that you occupy, right? And you ask the question, how many different ways can I arrange a volume of space that size, right? What is you're one arrangement, right? I'm another arrangement, right? A cow is another arrangement. Empty space is another arrangement. There's lots of different possible arrangements that are, let's say, roughly a cubic meter of space could occupy, could be in, sorry. And so the question is, how many arrangements are there? And of course, as the universe gets, and then you can sort of imagine yourself, so it's some number, some very big number. There's lots of possible. Is it infinite though? That's the real question. Is there an infinite possible ways in which you can arrange a cubic meter of space? And so that's the key question. The answer to that is it's not infinite. And there's a reason why it's not infinite. There's two reasons actually why it's not infinite. One is quantum mechanics, and the other one is gravity. Those two ingredients guarantee that number is not infinite. Quantum mechanics kind of discretizes things all over space, and it gives you a sort of a building block. That gives you almost straight away a finite piece. And also gravity itself, that's space-time. And so when we talk about quantum gravity, we can think about breaking up space-time in a finite way. So straight away, we've got this arrangement of a cubic meter of space. We can go into that into more detail. And the number of ways in which you can arrange it are finite. It's a finite but very large number. Now, but if the universe is big enough, you can imagine sort of, I start off with you, Robinson, one arrangement of that cubic meter of space. I then go alongside you, and I sample the next arrangement, and it's different. Okay, so I've now sampled two, and I keep moving across this gigantic universe, and I keep sampling these cubic meters of space. Now, eventually, I'm going to move through so many possibilities that I will start to see repetitions. Now, you might say, well, okay, fine, but you're going to see the more likely repetitions first. Of course, that's obviously true. Not everything is equally likely. I mean, I would absolutely, for example, empty space is going to be far more likely than a Robinson, right? Clearly true. But Robinson is clearly not vanishingly unlikely. Okay? And actually, if you go to sufficiently large universes, then even the unlikely things will start to repeat. It's just like, it's just inevitable. And this is one of the ways in which I try to sort of imagine a Googleplex and how big a Googleplex really is. That if you imagine a universe that's a Googleplex meters across, then actually the chance that you would have to be almost essentially vanishingly unlikely not to have a doppelganger somewhere in a Googleplex universe, which is remarkable, right?
It is. Let's, if it's okay with you, let's get into the arrangements of space in more detail. And why does entropy figure into how you think about this question? And first, I might ask you to explain just how you think about entropy, since you write that most people introduce it as analogous to a measure of disorder, but that this is it's imprecise. Maybe it's not the right way of looking at it.
Yeah, I mean, that's the standard story, right? And I know it's not a terrible way to describe it. It's fine for its purpose. But so for example, just to flow with that a second, people will talk about a bedroom. A tidy bedroom has a low entropy, and a messy room has a higher entropy because it's more disordered. Well, actually, do you know what? That's true in a way, but let's try to unpick that a little bit to try to better understand what entropy really is. So let's suppose you have a tidy room, right? And you've got a bed arranged really nicely. There's a teddy bear sat on the bed. There's an alarm clock next to the bed. There's a book there maybe. Okay, now you run into the room and you look at it. And you've got 2 seconds to just absorb the information and figure out what's in the room. Okay, and where it is. Now, because the room's nice and tidy, and then somebody shows you a picture of another room, and you've got to say, is that the same room? You probably got to do a pretty good job of getting that right? Because you knew the teddy was there. You saw the teddy. You saw the alarm clock. You saw the book. And it was all organized, and you were able to sort of distinguish this room from another room that is different, right? That has perhaps the teddy in a different place, or the alarm clock showing a different time, or a different book, So you can tell the difference, okay? But suppose you do something. Suppose that room is not a tidy room. Suppose it's a messy room. Stuff strewn everywhere. Teddy's there, but it's under a pile of clothes. It's a little bit of it sticking out. Alarm clock's just, got glasses in front of it. The whole thing's chaotic, right? And now you do the same trick and you run into the room and you do your 2 second, sort of recording what you see. And then somebody shows you another room, which is similarly messy. And you've got to figure out, is it the same room? But maybe the only thing different is the teddy was moved to a slightly different place. But because it's such a mess, you can't tell. It just looks like the same room. That's really, so that's why it has a higher entropy. So what I'm really getting at here is entropy is really the number of different ways in which you can sort of kind of average something, in which you can get something to look the same. Okay? So let me give you another example. So an egg, take an egg, literally an egg. So you can ask, well, this has got entropy. Now why? Why has it got entropy? Because I look at the egg, right, and I see it's an egg. It's a certain size, it's a certain weight, a certain temperature, it looks a certain way, right? Now there's loads of missing information that I don't see. The specific arrangement of all the atoms within the egg, all that detail. Now that's detail I'm sort of washing away. It's like the detail of the messy room, of how the clothes were strewn everywhere. It's that detail. You don't worry about that detail. You kind of average it out. Your brain sort of just washes it away. And so when you're looking at the egg, you're not worrying about all the arrangements of all the different atoms. Now you might have another, so to describe that egg and describe it, the level of approximation you're willing to do, There might be lots of equivalent things that essentially, as far as you're concerned, are exactly the same egg, because you don't care about the arrangements of the atoms. You're not measuring that. You're measuring these macroscopic quantities, and there might be lots and lots and lots of different microscopic arrangements that yield the same macroscopic egg, right? And so entropy is really counting all those different possible microscopic arrangements. That's what it is. We call them microstates. It's counting all the different possibilities that give the same macroscopic output. So in the case of an egg, it's just like, it's all those different possible ways you could have arranged the atoms. They still get the same egg as far as you're concerned. In the case of the bedroom, it's all the different possible messy arrangements of the clothes and all that you just don't sort of disentangle. Now, that's what it is. It's all those different microscopic ingredients. So entropy, in some sense, is a measure of missing information. It's a measure of the number of ways, the hidden ways in which you can arrange something. And so that's why it's important for counting the number of ways in which I can arrange a cubic meter of space.
This, though, I'm not sure is going to connect necessarily with our question of doppelgangers, but another conception of entropy that you introduce is that, unless I'm mixing books up, I don't think I am, but it's that of a jailer holding back energy. And how does this picture connect with the microstate, macrostate idea?
Yeah, so it's yeah. So I think I give sort of an analogy in my book about somebody breaking into a house, and so this goes back to the original idea of entropy and the sort of idea of change in a system. And the transfer of heat in particular. You're thinking about how heat transfers from one place to another, and what's really the agent of that change? What is entropy? It's the growth of the number of states in the system. So you can think about entropy as the agent of heat transfer, and that's how it was originally formulated back in the day, in the Victorian times, by those early physicists. And of course, it was Boltzmann that came along and then understood that this was actually the growth of the number of states of the system. But one of the things that we know is that if you have a system of heat transfer, that as you eliminate the sort of gradient in the heat gradient in temperature, then you shut down heat transfer. There's nothing else to do. Right. And so the growth of entropy is related to this desire to sort of shut down the amount of available work there is in the universe. So it's trying to shut down all these gradients. So, you can try to generate, move energy from one place to another. But what the growth of entropy does is it tries to shut that down. It tries to slow that process down. So the way you can think of it as somebody breaking into a house. And this burglar is trying to sort of take out, trying to go through the house and sort of take out all the, as much of the jewels as they like. But ultimately, as everything just grows, the number of room grows, it just becomes harder process for it to drag this stuff out. I don't know if that's a perfect analogy, but that's it. What Boltzmann realized was this change of the system was related to this shutting down of work, of available energy, was related to the growth of the microstates of the system. That it's just there's fewer places. You're using up all the possibilities in some sense.
Okay, no, great. That connects the two. No, it's very helpful. And before we turn to the Googleplexian metric of size of the universe, I'd like to still better understand the composition or configuration of our doppelgängers. So you already alluded to this, but how does quantum indeterminacy affect whether there can be a true doppelganger to you or me, or if we're even determinate things to begin with? I guess I'm wondering what the final number is you arrive at for how many different possible configurations there are of a volume of my size or something like that.
Yeah. So I mean, again, this kind of relates to how much information we want to wash away and not worry about. Do we average over the state of electrons in your small intestine? Is that something we want to wash away, or not? Right. Actually, so when I do the estimate in the book, I end up not washing those things away. I literally think of you as a pure quantum state. Now, it's a strange thing to do because in some sense, you are in some sense a pure quantum state, but nobody's ever going to really think of you like that because I never measure all your degrees of freedom. I don't measure those electrons in your small intestine. I don't do it. I don't know them. I'm averaging over them. Any measurements I do of you is averaging over those possibilities. And so I don't really think of you as a pure quantum state. I think of you as actually really is a mixed quantum state, where I wash away those possibilities and I average over them. But in truth, I can think of you as a pure quantum state, and in some sense, you are one. And so if I do that, I can ask how many pure quantum states can there possibly be in a cubic meter of space? And I can do that calculation based on my understanding of gravity and the counting of degrees of freedom, the counting of those ingredients. And maybe that's something we can go into now, but that's how I do it.
Okay. And do you recall roughly what the number you come up with is?
Oh, I think it's 10 to the 10 to the 69, something like that.
Okay.
It's something
so
like
massive. I think that's probably sufficient.
It's massive, right? But what's interesting is it's way less than a Googleplex. It's like ridiculously big. Okay, so what's a Googleplex, right? So a Google is a one with 100 zeros, and a Googleplex is a one with a Google zeros. So of course, 10 to the 69 is less than a Google. And so I think this it's something around, I might be 10 to 68, but so 10 to 69 is less than a Google. And so, so one with 69 zeros, and I'm talking about one with that many zeros. So it's way less than a Googleplex. It's a much smaller number. And that's the key point. That's the point, that it's much, even though it's massive, it's way smaller than a Googleplex.
And when most people speak of the universe, I think they're implicitly talking about the observable universe. And I think it would behoove us to explain just what the observable universe is and how big it is.
Yeah, so yeah, you're absolutely right. So I'm not talking about observable universe when I talk about Googleplexian universe. So just to be clear on that, I'm talking about something much larger. So the observable universe is about 10 to the 26 meters across, if I remember rightly. So that's the one with 26 zeros meters. Big, but certainly nothing. There's no Googleplexes floating around in that number. That's very small compared to a Googleplex. And so what is that? So that is essentially, it's kind of as far as the eye could see, is the way I like to sort of describe it. So you think about, so the universe has lived for a finite time. It had a beginning about 13.8 billion years ago. It's been growing in that time. And there's a limit to the distance that light could have traveled in that period. And so there's a region beyond that 10 to 26 meters where the stuff is literally so far away from us. We're not in causal contact with it in any way. So in other words, there's no way we could have ever exchanged a signal. Right, it's too far away. It's we can't see that stuff. To have communicated with that stuff beyond that distance, the light would have had to travel faster than the speed of light, and that's the limit. So that's kind of the sense. So there's this boundary, there's this shroud around us, around 10 to 26 meters, beyond which everything beyond it is too far away from us for us to have any, for light to have traveled to, for light from it to have reached us since the universe began.
Right. And my understanding is that physicists have no doubt that there is stuff beyond the observable universe. But does cosmology currently give any indication of how much stuff there might be or how big the universe could be? Or is this something that we're totally in the dark about?
No, it does. It does actually. So one of the things you can think about when you think about you can think about the shape of the universe. Now, so typically we assume that the universe looks the same everywhere and in all directions. It's called homogeneity, and isotropy is the buzzword that we use to describe that. But what that tells us actually, if you make that assumption, it's a good assumption on very large scales. That basically it looks the same everywhere. That means the shape of the universe doesn't have there's not many possibilities for its shape. And one of the things you can imagine is that its shape is it's like a giant sphere in some sense. It's a three-dimensional surface of a sphere, but it's like a giant sphere. So you could imagine it's finite, and you could go all the way around and come back to where you started with, right? So it's a huge sphere, okay? Or it's like a plane, or it's even like a saddle. These are the three possibilities. Now, the question is the object is that shape infinite, or is it finite? Well, if it's a sphere, it's certainly finite, okay? Spheres are finite. So if the universe is a giant sphere and you could sort of go across the universe and travel for billions and billions of years and come all the way back to where you started from, literally, like navigating the surface of the Earth, but doing it on a cosmic scale. So you can ask the question, do we measure that shape of the universe? And we do. We measure it with the cosmic microwave background radiation, which is this sort of radiation that's left over from the Big Bang. And we can look because the photons that make up that radiation, they travel through the universe and they feel its shape as they move through it, and we can detect that in the spectrum of the radiation. So that's what we do. We're able to put bounds on the on the shape of the universe, and what we know is that it could be a sphere, it could be a giant sphere, but if it is a giant sphere, it's a really, 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 really big one. So big that it looks flat to us, so we can't even tell the difference between it, whether it's we're in a sphere or actually we're just in a plane, because its sphere is so big. Well, how big must it be? Well, it must be, I think the number is in my book, but I remember, I think it's about 250 times bigger than the observable universe. It's got to be really big. So we know it's not. So that's kind of like, we know the universe is maybe of order 100 times bigger than the observable size. How much bigger it is than that, we don't know. We don't have an upper limit. It could, in fact, be infinite. We don't know.
And then before we calculate or talk about the distance, I have one. You said that when I gave my sort of naive formulation of the problem, you said that you didn't agree with my suggestion that mass was important. And I just wanted to clarify that, because if we're looking for my doppelganger out there, if there's far more mass in a region, then it seems much more likely that we would find a doppelganger of me there, because trivially, if there's no mass, there's no chance. So the density of the mass in the non-observable universe would be a very important number, as far as I can tell, if we're trying to figure out if my doppelganger's out there. Because if it's empty, then there just wouldn't be a doppelganger at all.
I mean, obviously, you're saying that because you yourself carry mass, and therefore doppelganger must carry mass. So you can't have a situation where you have vanishingly small densities. Clearly, that's true, but I think it emphasizes the wrong point. I think the point is really how many possibilities there are, and then you can ask so you take your cubic meter of space and you ask how many different ways different quantum states can describe that cubic meter of space. It's a large number. I think it's 10 to the 10. I think it's 10 to the 70. And then you can say, well, there's 10 to 70 possibilities. How far, so you're going to then start to move across space and start sampling these possibilities. And eventually you will see repetitions, maybe not repetitions of you, but repetitions of more likely things. But then eventually even the unlikely things start to be repeated. So you can actually do a calculation of, well, how unlikely do you have to be to not for there not to be for there to be only one of you in a universe as a Google Plex meters across, and the number is tiny. You'd have to be ridiculously tiny, smaller than any other number. It's just really, really small number. It makes it implausibly. I mean, it could be that you're that unlikely, and we're all very special, but it's hard to justify it, I think.
Okay, and then it seems like a Googleplex this is a number within which, given the parameters we've discussed, it's very, very you're going to find Doppelgängers. But is there a more specific number, where you think this is probably about the distance it would be that you'd find one Doppelgänger?
So this is where you relate it to the number of different combinations. Let's now the moment to start thinking a bit more about the calculation. So the calculation uses black holes. Okay, so it turns out that the black holes are the best storers of entropy in the universe. They're the best hiders of information. And it's kind of really, you can think of this quite intuitively, actually. So when we talk about a black hole, there's only certain things that we can measure about it. We measure its mass, its charge, and its spin. It's famous saying that black holes have no hair. There's no bumps and bruises on a black hole. We just measure their mass, their charge, and their spin. So you can ask a question, right? Suppose you wake up one morning and there's a black hole in your garden. You're like, oh, this black hole just appeared in my garden. And you measure its mass, its charge, and its spin. Don't get too close, because it's probably not a very big black hole, and small black holes are the dangerous ones. But anyway, so then the next day, you notice that black hole has changed by the mass of an elephant. So it's grown a little bit, and it's changed its mass by the mass of an elephant. But you actually say, well, what's happened to that black hole? Has it swallowed an elephant? And you don't know. Maybe it's not giving up that information. It could have swallowed an elephant, but it could have swallowed a car that's got the same mass, and you can't tell because it's not giving up that information. It's hiding that information. That's now becoming entropy in some sense. So black holes carry huge. They're the best hiders of information in the universe, and they do carry entropy. They carry a lot of entropy for their size, and so. One of the things you can do is you can do an experiment. You can think about, like a thought experiment. You can think about, if you start off with take a cubic meter of space. What's the most entropy you can cram into that cubic meter of space? Well, it's the black hole that fills the space. Because black holes are the best. They're better than me and you at storing entropy. They're deeply gravitational objects. And so how much entropy can a black hole store? It literally is the best hide of information. And its entropy it goes like the surface area. It goes like the area, its surface area in units of the Planck length, which is a really tiny distance scale. So it turns out that for a cubic meter of space, you're going to get about 10. The entropy is going to be about 10 to the 70 of the corresponding black hole. Okay, so 1 with 70 zeros, that's its entropy. And the entropy is in turn the log of the number of possible microstates. So you can just exponentiate it and you get the number of microstates down. And so this then leads to the idea that we have this sort of kind of holographic image of the universe in some sense, that the degrees of freedom that you can use to describe, the ingredients you use to describe a cubic meter of space, you can think of as being kind of sort of stored on the edge of that space. And the number of degrees of freedom that you need, the number of ingredients you need is going to be e to the 10 to the 70, which I think is about 10 to the 10 to the 68 or 69 or something. And so that's counting the number of microstates that you have, right, that can describe a cubic meter of space. And it's no more. If you wanted it to be more, there's two things you could do. You could reduce what's called the Planck length, the length at which space-time breaks down and becomes quantum. You could reduce that, then the number would go up. Or you could sort of not have quantum mechanics, right? If you didn't have quantum mechanics, then you wouldn't be breaking this up. What quantum mechanics does is it discretizes everything. It turns them into quanta, right? You wouldn't have that. You'd have like continuums. And so the minute you go from discretum to continuum, then suddenly, finite quantities become infinite. And again, you'd have infinite number of possibilities. But we do have quantum mechanics and we do have gravity. We do have a finite Planck length. And so all these things together tell us that that cubic meter of space only has a finite number of possible quantum states that can describe it. Now, of course, I'm making the assumption here that the physics doesn't change as I move across the universe. So in some sense, there's some sort of locality argument here, right? That there's a consistency in the physical laws as I move vast distances in the universe. And you could argue about whether that's justified or not. But if I assume it, then indeed, then as I move through the steps and move across the universe, then eventually you'll start to see repetitions of those 10 to the 68 or 69 possible states. So that's kind of the number, I think. Now, I think if I said I had a universe which was 10 to the 68, 69 meters across, it would be a stretch to say that you had a doppelganger. That's a rough ballpark estimate for the distance to your doppelganger, but it's probably, I now need to start to factor in that you're quite an unlikely thing, right? You're quite an unlikely cubic meter of space. So you have to so you really have to sort of absolutely swamp that number to start making grand claims about the existence of doppelgangers. But yeah, that's kind of the key number. I think I call it a doppelgangian, but it's probably a stretch to say that that's the distance to the doppelganger. Well, again, that depends on how you define a doppelganger. If you start averaging over internal degrees of freedom and you start not worrying about arrangements of electrons and so on and so forth, then the number will come down because you're not requiring such an exact match, of course. So there's swings and roundabouts here. You can make if you don't require such a precise equality to be a doppelganger, then you don't have to traverse such large distances.
Well, the last question I will ask about this is, do you really think that your doppelganger is out there somewhere? Is that something that you'd like gun to your head you would just say? You'd be willing to put your money there?
That's a good question. I don't know. That's not a satisfactory answer, is it?
No. It's okay. I mean,
if it is, it doesn't matter because I'm never going to meet it because it's so far away. It's in a realm of the universe which is just never going to have anything to do with me, right? So it's not a thing, right? So it's just, it may be out there. It may be talking to another Robinson somewhere, maybe. I'm never going to interact with it. I'm never going to be able to do a physical experiment that involves it. It's kind of removed. Do I believe it's there? I think it's plausible that the universe could be so large. So when you start to think about that, then maybe. I think I talk a little bit in the book about eternal inflation and trying to understand the initial conditions of the universe, why the universe started out as it did, and the idea of this sort of field jumping about in the early universe and causing the universe to grow, pockets of the universe to grow very, very quickly. And it continues to do this eternally and forever in all different pockets of the universe. Now, such a universe would be huge, truly gargantuan. So it's in that scenario, you can imagine that, well, maybe. So yeah, I don't want to say, I don't know is such an unsatisfactory answer, but the sort of the physicist in me just doesn't want to say yes, it's one or the other. So I'm going to say on the fence.